The last part of this topic is looking at practical questions that might involve boxes like this one, plots on a farm, the cost of petrol on a trip, practical applications of maxima and minima. Now, in every question, there's a certain method to doing these, which I'll do in a minute. But we'll read this question and then I'll highlight what's common in every single one of these questions. So in this one, it's about a box, and it's a good idea to draw a diagram if there's not one given. A box is made from an 80 centimetre by 30 centimetre rectangle of cardboard. So that's pictured by cutting out 4 equal squares of side X from each corner. So basically, that's going to go, that's going to go, that's going to go, and that's going to go, and we'll fold the box up. The edges are turned up to make an open box. Show that the volume of the box is given by that equation. Find the value of X that gives its greatest volume, and then find the maximum volume. So this question kind of leads you through it. They don't all do that. So if they don't, the question could simply be, find the maximum volume of the box. So step 1 is to decide what is being maximised or minimised. And in this case it's volume. So we need an equation for volume. So in this case, volume of the box. So we need to look at the length by the width by the height and get some dimensions for that. Step 2 is to find the extra bit of information, because that enables us to eliminate one of the variables. So find the extra bit of information. Because if you think about it, in this case, volume is length by the width by the height. So we've got numbers and it's in terms of X, so that's okay. And in this case, there's already enough information for us to eliminate that variable. So we'll do another one in a minute where it doesn't lead you quite so easily through it. Third step is to write an equation for the property that's being maximised or minimised. And in this case it's volume. Fourth step is to eliminate the extra variable using the extra information. Fifth step is to derive the equation. 6. Let the derivative, let's call it y dash, equals 0 to find stationary points. Point or points. Now, having said that, sometimes you do get 2 or even 3 stationary points, and you'll have to be able to eliminate 2 of them. For instance, if one of them comes out to be 0, and it's the dimensions of a box, obviously that can't work, or a negative. So sometimes you do get more than one, but only one will work. Step 7 is to find the second derivative and prove that the stationary point is either a max or a min, as said in the question. whichever one's appropriate. And the 8th part's the important part, and that's answer the question. That sounds silly, but if you have a look at a lot of these questions, some of them, for instance, if they're talking about a box, simply ask you for the dimensions. Others ask you for the volume, given that it's a maximum with those dimensions. So you must answer the question at the end. And part 7 is very important. You can't assume just because they've told you that it's a max or a mean. You need to sub it into the second derivative and actually show that. So let's attempt this question now on the next page. Okay, I'm going to draw the box, actually construct it, because I find it easier to look at the volume from this perspective. Now, if we think about the length, the original question said that the piece of cardboard was 80 centimetres, but we cut out 2 bits of x to fold the box up. So therefore the length is now 80 minus 2x centimetres, and the height was the same, it's 30 minus 2x. Sorry, not the height, the width. 30 minus 2x. And if you think about that box being built up, how high will it stand? It'll just be x, because that's the cutout bits. So that's our volume. Now we look at that, and if there's more than one variable, we need that extra bit of information. However, in here, there's just in terms of x, so we're okay. So, if you have a look at the question, it's the volume that they're after, the greatest volume. And part A asks us to write an equation for volume. So volume equals length by width by height, and sub in what you've got. And again, if there's 2 variables on the right hand side, then you need to substitute by using that extra bit of information. So it's 80 minus 2x, 30 minus 2x, and x. And that's good enough, except that that's not the way it's written in the question. So we need to expand it out. So that's 2400 minus 160x minus 60x plus 4x squared. And we're going to times all that by x. I'm just going to move it over there a little bit. So that's 2400x. And in the brackets we've got minus 160 minus another 60. So that's minus 220x. And then I multiply it by x, so it's x squared. And plus 4x cubed. And if that's the same now, it doesn't have to be in the same order as the equation, but if we've got the correct terms in that expression, in that equation, then that's good. So we can hashtag that. Probably should go back to black. Next. Find the value of x that gives the box its greatest volume. When you see the word greatest, biggest, largest, that's all talking about max. So max is greatest, biggest, largest. There's probably some other words there as well. And minimum, if they say the smallest, or another one for max would be the most, and least for smallest, smallest, least, can't think of any more at the moment, but that would be the minimum. So in this case it's a maximum. And I just realised that's an x squared there. Minus 220x times x is 220x squared. Okay, so on the next page we're going to derive it to find the stationary point. So if we derive that, v dash is 12x squared minus 440x plus 2400. And let v dash equal 0 to find the stationary points. So 12x squared minus 440x plus 2400 equals 0. Factorising that, I can take a 4 out. And I'm left with 3x squared minus 110x plus 600 equals 0. Now I did this one by the quadratic formula. You can try and factorise it, but I thought it looks quite low. So I got out of the quadratic formula that x equals, there's two answers, 30 and also 40 on 6, or 6 2/3. So this is an example of one where we've got two answers, because it is a cubic, so there would be two turning points with any luck. And so now we need to check the second derivative for both of those and find out which one's the maximum, as that's what the question asked. So the second derivative is 24 minus 440x. And if I sub in x equals 30, I get that the second derivative is 24 by 30 minus 440, which equals 280, which is bigger than 0, so it's actually a minimum. That's not the one we want. If x equals 40 on 6, we get that the second derivative is 24 times 40 on 6 minus 440, and that gives us minus 280, which is the one we want. So less than 0, so it's a max. So our stationary point is 40 on 6. So part B, the question said find the value of x that gives the box its greatest maximum. Well, when x equals 40 on x, the box has greatest volume. And part C said actually find that volume. So we've already got the volume equation that we proved in part A. 220x squared, wasn't it? Plus 2400x. And we've found our x, so what we need to do is sub in 40 on 6 into the equation to get that maximum volume. And that comes to a grand total of 7407 point, let's go for 1. I'm not quite sure what the question asked. Oops, that's a cubed. No, I just checked the question. It didn't give any specifications. So I'm going to do it to 2 decimal places. And the units are centimetres cubed. So that's our first example. And the next video will show another example.